Welcome back to our NSF PI's meeting. We'll have the second keynote on spectrum challenges in the 5G and 6G era. It's my pleasure to welcome Professor Mischa Dohler. He is the VP of Emerging Technologies at Ericsson. In Silicon Valley, he serves on the Spectrum Advisory Board of Ofcom and served on the Technical Advisory Committee of the FCC. He's a fellow of the IEEE, the Royal Academy of Engineering, the Royal Society of Arts, the Institution of Engineering and Technology, and the distinguished member of Harvard Square Leaders Excellence. He's a serial entrepreneur with 5 companies. He's a composer and a pianist with 5 albums. Fluent in several languages. He has pioneered several research fields, contributed to numerous wireless broadband, IoT and cybersecurity standards, and holds a dozen patents, organized and chaired numerous conferences. He's a top 1% cited innovator across all science fields globally, and he was professor in wireless communications at King's College London and director of the Center for Telecommunications Research from 2013 to 2021. Without further ado, Mr. Dohler.
So I've rejoined the dark side. I've gone back to industry. I thought I'll give you a little bit of an overview on how we see the spectrum challenges from an industrial point of view. I'll try to phrase it in such a way that the academics in the room, the students, can actually make sense out of this and help us. It's actually a plea for help, to be honest, on the issues I'll talk through today. First thing, big elephant in the room. I want to explain to you a little bit why we are so religious about the mid-band. So the mid-band is from 2 to 6 and actually going up now to higher bands, why we really want that. So let's have a look on how traffic has been growing last years. And as a little engineering shop, we have been doing these predictions for years. We've always been spot on, if not very conservative, very often how traffic will evolve. And as of 2024, we are using our smartphones. Fixed wireless access has become a surprise hit in the 5G era. XR is coming. You have heard about the Quest 3 announcements of the Vision Pro by Apple. This will hit us very hard from a capacity point of view very soon. But there's other stuff happening as well. Those who know my work, I've been working for maybe 8 years now on a 5G-enabled telesurgery use case. I got a lot of heat back then. Nobody believed this makes sense at all. But actually, we are implementing it right now. I'm working with the FDA. I'm working with surgeons, the White House, to make that a real commercial proposition here in the United States. So that traffic will be adding up. And this is not the end of it. New stuff is coming. The new kid on the block is Gen AI. We have loads of AI use cases. We talk a lot about AI native 5G, 6G, but generative AI will be the real disruptor. What does that mean from a traffic point of view? What does it mean when you have an agent doing stuff for you on your mobile phone? What happens if you use Gen AI to compress images using semantic comms, expand it, etc.? What is the impact on the network? It doesn't stop there. If you look at the more machine-centric ecosystem, it goes beyond IoT. We'll see a lot of flying saucers in the skies very soon. West Coast, where I'm based at the moment, loads of drone companies working on flying taxis. So these are not small drones you're used to today. These are literally the Ubers of tomorrow. And they're getting their licenses from the FAA. And once you're in the air, most likely you will not be piloting the thing. You'll be bored. You need to do something as you fly in the sky. And guess what? We need to connect you. So then we need connectivity. But there's more stuff coming. Robots, droids. And you think this is a far-fetched future? Just visit me in Silicon Valley and I'll show you around all the companies who are building droid systems today. NVIDIA just released a completely new tool package, Groot, which enables acceleration of innovation in that space. Need to connect it all. It looks very problematic from a traffic point of view. So if we were to connect it at home using Wi-Fi, there's no problem. Doing this wide scale at national level in the skies, we have a problem, Houston. There's a real problem there. We need to see how we go about this. Even the most conservative prediction says 3x by the end of the decade. Most conservative. We do not count XR. We do not count fixed wireless access. We do not count the droids walking the streets possibly in 10 years. So we do have a real problem there on how we get that capacity addressed. But we are also looking at how can we solve it, right? So how can we connect all these new use cases towards the end of the decade? And as an engineer, we can do three things. The very first thing you can do is you can upgrade your base stations, your gear. You can implement new interference cancellation mechanisms, new MIMO code books, more antennas. You can do that. That's your job. That's our job from a vendor ecosystem to implement that. Having said that, we're pretty close to the Shannon limit. So there's very little we can do to squeeze that further. We're really hitting now the hard boundaries. Okay, the last frontier is maybe now with semantic comms, but that's about it. Okay, so then we have the second thing is you could say, hey, why don't we densify? Right, so we increase what we call the ISD, the intersite distance, to something which is smaller, because then you got Maxwell kicking in and you get more power and it should work really nicely. So the issue here is the economics. So you at some point the operators can't just print money; they have to look at their balance sheet, and they need to. You can't just densify infinitely, right? So, and I'm showing this on this chart here. We've done the analysis, actually real data from the United States with real spectrum. So these are not fictitious numbers. You see a low band there. You would deploy one base station, covers a huge area, but very low capacity. So not very useful for you to flick through your TikTok and your Instagram reels, right? So then we got the mid band, and there you would deploy about 30 base stations to get the same effect. You have more capacity, and to get the very same coverage as the low band, 30 base stations, okay? And as you go then into the high bands, it's several thousand base stations, right? So you need to, it's not just putting them on the roof, it's also connecting fiber, maintaining them. And in fact, it's the highest cost to the operator. So the best we can do today is the mid-band, full stop. Today, I'm saying today, because 20 years ago, we thought mid-band was impossible. We were in the low band. Look where we are now. So therefore, at some point, we will probably go in the higher bands. But the plea I have today is for today in the next 10 years. Okay, that's really what I would like us to sort out. So, and the third thing to deal with that is spectrum. So really getting more mid-band spectrum, I think, will do the trick. And that's the allocation today. So I just gave a tutorial of Charles from the NTIA, with Ira from the FCC, and Monisha, who's a former CTO of the FCC. And I was pushed back on this chart here that the numbers aren't really correct. It doesn't really matter how much these numbers, they will fluctuate a little bit. Fact is that you have three big ecosystems. You got the federal ecosystem, national security, radars, a lot of other federal services as well, and they have about 2 gig, if I see that right. So about 2 gigahertz of spectrum, right? And then you got license exempt, mainly, let's say, Wi-Fi. We're using this today. That's about 2 gig as well. And then we got cellular, which has a quarter of that today, about a quarter of that. And to make it more interesting is, whilst the federal users protect you as an individual citizen, okay, at 2 gigahertz bandwidth, whilst you as an individual citizen could in theory use 2 gigahertz Wi-Fi, you as an individual citizen cannot use 500 megahertz of spectrum because it's a competitive space. There are 3 operators, so using a third of that, which is why you understand is when you're flicking through your Instagram reel, it works really well in the building with Wi-Fi, and it doesn't work at all in many places outdoors. That's the real reason. We have a spectrum imbalance there, and we need to deal with that somehow. And policies are needed, and if we do it right, we get the right economic growth, right? So we have seen a fantastic growth there, from the telco industry, and we hope in the 6G era it will do the same trick. Wi-Fi industry is contributing massively as well. So I think as a cellular industry, we recognize the value of Wi-Fi. 80% of the traffic is happening indoors, 20% outdoors. We're trying to equalize a little bit that outdoors game. Okay, so that's really what we want to do. Now, the outdoors game is now a 5G game, will soon be a 6G game. So let me just talk you through very quickly where we are with 6G. So some of you might have been exposed to this, famous triangle of the 3GPP ecosystem on the different use cases. So it's we're using very unpronounceable acronyms, right? So it's actually almost only the telco ecosystem does it. EMBB stands for Enhanced Mobile Broadband. It means a YouTube video on your phone. Then we have URLC. It is the ultra reliable low latency comms. This is to make sure you can connect factories, very reliable type of systems. And the MIT is the massive, or MMTC, I'm not sure what's put there, I don't have my glasses, massive IoT or massive machine type communications is all about smart cities, smart farming and all that. We had this. 5G Advanced, we expanded the capabilities. We really made sure it works better, faster, more reliable. And in 6G, we keep that actually. So if you look at the lower part of the chart, you see these three constituents there. We're keeping that, but there's new stuff coming. Okay, and the biggest new thing is probably XR, so augmented reality, most likely the most prominent use case outdoors, but even VR, apparently 5G now with the Vision Pro, we just got the data, turns out a lot of people who bought the Vision Pro are tethering it to 5G, so who knows, I don't really believe in it, but the market may say otherwise. So we have XR coming out there, and that in 6G will be a huge use case. To make that work, we need integrated sensing and communications, which is, that use case which allows me to really understand what's the spatial surrounding in the room here to project the right content. And you may have seen Apple announce a partnership with Disney at the launch of the Vision Pro, and they just put out content, it's going to come in the next weeks, where you actually put on the Vision Pro and you see the movie, which is really adapted to the environment. So if I watch a horror movie, this room would be dark, somebody would walk through the door, so it becomes so much more immersive than what we have actually envisaged. So we needed another new use case I learned from Monisha, actually, I'm not sure she's here in the room. She's using sensing to understand whether we're indoors or outdoors, which is quite useful in doing certain dynamic spectrum allocation policies. So she told me that's all published. So and AI, of course, is in the mix, is one of the other one. We talk quite a lot about this. Now, how do we go about building these systems? And the industry is just ticking, in one kind of bubble, and that is 3GPP. Whether you like it or you don't like it, the juice is happening there. And you have thousands of companies come together, trying to agree, reaching consensus. It is, of course, very difficult because we can't even reach a consensus between 2 or 3 people. Imagine now thousands of companies with real commercial interests. So the way it works is you do it in 3 phases. Right? So to lower a little bit of tension, you do it in 3 phases. The first phase is always, let's look at the requirements. Then you say, let's look at the, let's study what these requirements would yield. And the third phase is you implement it, right? You standardize it, you standardize it. So 6G has actually already started because the requirement work on 6G is part of release 19, which has just started. So 6G is a real thing. It's not something in the future happening right now. Once release 19 is frozen, we get to release 20 mid of next year when the study items will. So we take the requirements and then we say, hey, what does that mean really from a simulation point of view, capacity point of view, all that. And after that, the good things are being taken and we start standardizing, writing the requirements, okay? So that's happening. That pipeline is there. And then we have the spectrum pipeline. WRC 23 was a big event. No spectrum was allocated. Again, we just discussed what type of spectrum should be studied. So we have now 4 years to agree on, the simulation models, Maxwell equations, which I thought are immutable, but here we go. So we have now 4 years to really figure out whether, these bands can be, should be, will be used. And WRC will be used to fix them. Okay? And then we have, of course, the regulatory aspect, make sure we don't make this too fragmented. Now, 6G is real, and I wanted to show you a few proof of concepts. From Ericsson's side, we're not the only ones. Our competitors are doing things, our partners doing things, but I wanted to show you at least what we're doing. 2 ends of the spectrum. So one end is really low power, in fact, not low power, 0 power. Okay, so we engaged with MIT maybe 5 years ago, and we gave them a task which we thought was impossible. We told them, design as an IoT sensor which consumes 0 joule, no battery. Okay, and they did it. So I maintain, if we give academics the right question, they'll come up with the right solution. All right, so therefore, please listen to my subsequent slides because there are 2 or 3 things I would like you to solve And I'm sure your intellectual firepower is good enough to solve that for us. But they did it. And it's become now the work stream of IoT-A, if anybody is in 3GPP, IoT, the ambient IoT, completely changing the way how we will be connecting sensors in the future. Zero battery. It's fantastic, right? 3GPP compliant in the future. Then we have, on the other end, we have extremely high data rate, and we're talking about gigabits per second transmission. We built this prototype there. I was at Mobile World Congress. You've seen my picture there. It is what you're seeing there is the world's first 6G mobile phone. Okay, so I hope over the years we'll get it smaller, but the prototype is there. So therefore, it's getting real, it's happening. And the key ingredients we are using is really the stuff we've been talking about for quite a while. We're trying to make sure we get integrated sensing and comms really right. It's not an obvious thing. I thought it's pretty straightforward. You just use an OFDM waveform, try to understand what's the reflected channel impulse response, and you can actually deduce what's happening. But it turns out that a radar signature and a comms signature are very opposing. So coming up with a joint signature which works for both communities sufficiently well is an open challenge. So therefore, integrated sensing and comms is an open challenge. We have the MIMO challenges. We have the AI challenges. We're looking at, can we make the entire stack AI native? Can we actually have constellations which are designed on the run using AI? Okay, they're opposing views, and we are in the early days, but these are interesting things. A few lessons we learned from 6G as well is that we left the operators too much choice in deploying the way how they deployed 5G. So what you're using today, unless you're on one of the carriers, and I want to name the carrier, unless you're on one of the carriers, you actually have only a 4.9G system, truthfully, right? So the full 5G is not here yet, and they're still deploying that. So in 6G, they don't get that choice. So it's or 6G or it's no 6G is going to be one thing. But there's other thing coming. There are other ingredients coming. And I always talk, some of you have heard my keynotes before, they will remember I talk about the 3 Cs and the 3A. I always talk about supercharging 6G with AAA, right? So referring a little bit to the batteries, the AAA batteries, so we'll get a little bit of a boost there. So the 3 Cs we have today already is cyber, chips, and cloud, okay? A big constituent, really forming more and more discussion topics in the telco ecosystem, which before were either not public or were not there at all. Now, on the AAA side, you got AI, you got API, and you got AR. So there are lots of opportunities there. AI natively, or speaking about AI native systems, we're talking API from a monetization point of view. So AI is about efficiency, API is about monetization, and Ericsson just acquired a small shop in San Francisco called Vonage for $6 billion, which really cut into my salary, I have to admit. So we'll see how this plays out long term. But we put our stake. Our CEO said we take this strategic decision to really be serious about monetization in the 5G, 6G era, and we acquired Vonage. And AI, I talked about this a little bit. So we have that there. But the most important ingredient is spectrum. We are an untethered wireless industry. No spectrum, no industry. Full stop. So we always talk about this spectrum cake here, and you see the different services there. What I would like you to pay attention to is on the left-hand side, you see different colored arrows. So the green or the yellow, sorry, the yellow arrow is about low band, below 1 gigahertz. Think of it like a telemetry system for cellular. Think of it like your voice call support, really wide coverage. You put one base station, and we can cover a country like Luxembourg or the Vatican. We can't, of course, cover the US, but very few base stations get really good coverage. Then on the other side, you got up there in the red zone, you got millimeter wave, you got terahertz, and we understand you guys are really adamant about terahertz, and I understand. I was an academic. Terahertz, nobody published before. It's a great opportunity to boost your H index, but from an industry point of view, not a good timing. Okay, even WRC said the earliest we'll look at the W and D bands, which are the sub-gig bands, is WRC 31, not even 27, 31. Okay, So clearly we need a little bit of knowledge, but please focus your intellectual firepower into the bands we need, which is the green band. So it's all about the mid bands. I gave you the rationale before. It is all about the higher mid band, as we call it now, which goes from 7 to 15 gig, and we're still negotiating with the ecosystem. So let's dive into this and really try to understand what are the challenges. So what we really want to do is kind of equalize the game a little bit, okay? So give cellular a little bit more. Don't touch Wi-Fi. Wi-Fi is great. Maybe have the federal agencies agree to modernizing some of the infrastructure so they don't use it all they don't have this band all the time, even though they're not using it all the time. And it's not that straightforward. I'm simplifying the message massively. But, getting a bit of an equalized game there, because all three spectrums have their unique signature. So the federal spectrum is, on the problematic side, used very rarely, but it's used nationally, and when it's used, it has to be used. There's no question asked. Wi-Fi is used all the time, but almost nowhere. Now, you'll be surprised at me saying that, but if you normalize the total area of the United States versus where Wi-Fi is used, it's asymptotically zero. So it's used everywhere, almost nowhere, but huge economic value because we're using 80% where we are, okay? Now, cellular is using it less, 20%. It's using it nationally, it's using it also like Wi-Fi all the time. So each band is very different, okay, very different, and each band deserves an equal share of the pie. Now, the NTIA and the FCC have recognized it to one degree or another, and there's some serious efforts going on to actually equalize these bands, right? So we're talking about this pipeline here where some of these entries are factual, particularly those where you see a small text on the bottom of these vertical arrows, and others are postulates by my Spectrum folks and Ericsson based on international coverage. So what you see here is the timeline versus what the FCC and NTA are doing, almost like it will be doing, and you see a color code. So you see blue is, I can't see real with my glasses, so blue is, I think, the mid-band, green is the lower band, mid-band, higher mid-band, and then gray is the millimeter wave and above, right? So therefore, we have a pipeline now which is realistically, potentially giving us this equalizer, right? So think of it, I'm not sure you know the film Equalizer, think of it as Equalizer 4. So we are coming into this game. What are the challenges? Well, a lot of this, there is no spectrum free anymore. All right, so there is no pristine spectrum, so we need to share in one way or another. Everybody agrees with that. Okay, everybody agrees we need to share. So if you look at a 3 gig and 4 gig and part of the 7 gig spectrum here, I've shown it on the bottom, you see that it's occupied largely by federal services. They're super critical. There's radar in there. There is their comm service point to point, even 5G's in there. And how do we coexist now, right? Well, a lot of efforts are going on. When I worked in France Telecom 20 years ago, we worked on spectrum sharing. Then when I was at King's, we worked at spectrum sharing. So we've been doing this for quite a long time, and we still don't seem to get actually commercial solution out there, right? So, and I would like you to pay attention to one thing. I realized what the problem is, but I'll come to that. So we want to learn from from what has been done before. Spectrum sharing is not the first time we're doing this. We've done TV white space, we've done CBRS, we have done the C-band, and some other TV bands were actually repurposed or shared. Is a good learning there. So the colors here indicate a little bit on how the cellular industry thinks that whole thing went. My personal view is different. Okay, my personal view is different. Those who know my personal work, I work a lot on, as I said, on healthcare use cases, education community use cases. I maintain if a wireless connectivity has enabled to connect even a single school, it's a winning proposition. Okay, it's a winning proposition. TV white space has achieved that. CBRS has achieved that, and it's growing very quickly. And the other bands have achieved that as well. But I would like you to also go into the shoes of the cell industry. They look at this and say, look, guys, TV white space, CBRS, there's a lot of really good spectrum. And, if you had given this to us at regulatory requirements, which are not as stringent as they are today, we would have done so much more. We wouldn't have connected one school, 10 schools, 100 schools. We'd have connected the whole country, millions of people. So therefore, the wireless industry says, let's learn from, what went right, what went wrong. And there's one thing which stands out, and that is power. Okay, power stands out. It's not the sharing per se. The cellular community is actually the community which shares most. At millisecond level, do you know what's going on in these schedulers in the base station as you're trying to make a call or watch your Instagram reels? There is a decision on the sharing mechanisms going on at levels which no other industry has seen. So the sharing is not an issue. Okay, is not an issue. It is the power side. So economically, it makes no sense to deploy 4,000 base stations in an area where you could get away with 20 if you worked out a little bit the regime on how to do it. And we just didn't know how to do it. So therefore, all the regulators said, let's play very conservative. So my call to you, and you will hear this as a recurring theme for all the slides, start thinking how power. What type of research are you doing today which allows a coexistence with a high power cellular system? That's the only ask I have, all right? And with that in mind, let's just start jumping into some of these bands. So I'm going to talk about three bands, 3 gig, 4 gig, and 7 gig. By the way, everybody who's taking the photos of the slides, just email me. I'm going to send you the source files, okay? So you don't worry about this, all right? But it always looks good. Better take a picture of me because you don't get them in the slides. Just kidding. So anyway, 3 gig band, right? So a hugely contest. There's a lot going on in the 3 gig. In fact, we have Ambit going on, which is already licensed coexistence of an operator with federal services. We'll see how this plays out. We are hopeful. But from a tech point of view, we're interested in 3 things. The first thing we're interested in, what's the regulatory framework? Does the regulator allow us to use that band? Second thing we're worried about is what is 3GPP doing? Right? Has 3GPP standardized the bands? And the third thing is, what are the challenges which need to be overcome to make that happen? So from a regulatory point of view, actually, this band, has been mandated by Congress. The Wireless Innovation Regulation has stimulated that in the next 7 years, this band has to be shared, right? Whether you like a DoD or you don't, come up with a solution. It has to happen. It's been federally put in law now. So we need to get going, which is why all these innovation funds, NTIA, SpectrumX is falling in place to essentially follow that guideline which came out a few years back. Now, from a standardization point of view, hugely important. Do not underestimate this. And the reason is because Qualcomm will not design a chip. Ericsson will not design a chip if this is not part of the 3GPP bands agreed in the standards bodies, right? So, and it's only part of the 3 gig band which is currently standardized. So 3GPP still needs to come together, maybe in release 20, maybe in release 21, to agree on what are we going to do with this band, with the remainder of the band. If they don't do this, Qualcomm doesn't build it, Ericsson doesn't build it. And the reason is because there are a lot of technical challenges in here. You don't appreciate the millions of spectrum combinations you have in the chip today. It's all cramped in a very, very, very small device. And the same on the base station. Hugely complicated. How do you handle the filters? How do you handle the whole bandwidth? How do you handle the ADCs, power amplifiers, and all that? Depends very much on that standardization. And they're fighting blood, nail, and teeth in these standards buddies to agree whether these are bands we can do or we cannot do from a tech point of view. So this still needs to be done, but at least part of that is done. Now, from a challenge point of view, maybe the first challenge I would like to put out is let's agree on common models. I'm not sure how this can be in 2024, 200 years after my dear friend James Clerk Maxwell. By the way, James Clerk Maxwell discovered 3 of his equations at King's College in London, where I was professor for a decade. So I'm very dear to these equations, and we have all the same equations, but somehow when we walk into the ITU meetings, we have simulation results which differ by 10, 20 dB. How can this be? So we need these models. We need, you as an academic community, come up with a model where you can convince my friends in the cellular industry, with our partners in the Wi-Fi industry, with our dear colleagues in the defense industry, that really that's a common baseline. We don't have it yet, for reasons I cannot explain, but we don't have it, so we need that. It's a lower point. Then another one is about sharing, but you will be surprised, as I said before, we as a cellular industry, we're very good in sharing. Before you say, hey, you're sharing at millisecond level, so you should be able to do that with a radar. Well, yes and no. We can do it because we got millions of sensors in the streets. These are our phones. They give us through channel state information on the feedback. They tell us what to do. That's why we can do the scheduling. But when it comes to coexistence with radar, we don't have millions of sensors. So we need another solution there. But overall, databases, sensing, using the guard bands and the physical resource block allocation of 3GPP to do measurements, as we do today when we're trying to do the handovers or figure out whether there's another base station there. We can do this. This is not a challenge today, okay? So if I could ask you to tone down research on that and rather beef up research on the big elephant in the room, that is, how can a 50 dBm per 10 megahertz bandwidth cellular ecosystem coexist with a radar, coexist with a point-to-point federal service, coexist with a satellite, coexist with anything else which is in the bands, Wi-Fi including. That is a big challenge. And I know you can do it because you're all very smart. You've solved the impossible, so you will solve that too. So please start working on that. And I'm looking at the NSF as well. You're not really responsible for this budget, but whoever is, that's a big challenge you need to focus on, all right? Not whether we need a new database or new sensor or stuff like that. It's commercially solved. We can do that, no problem. Do it in a day. I'm exaggerating. My colleagues will kill me, but you get the idea, okay? 4 gig band. Now, 4 gig is super interesting because the US has not put forward this band as part of the spectrum pipeline. So we are postulating at some point it will hit the NTIA and or the FCC, mainly the NTIA, looking at what's in there. And the reason we think that's the case is because it has been considered at WRC. So it's now a global band, which I think, I can't read the number, if I remember well, is region 2, which is Europe and Africa. It's quite a big beast. So, if Europe is looking at this gig band, the US most likely will at some point follow because the challenges are very, very similar. So we're looking at this band. Again, I need to take my glasses here, apologies. We have 3GPP has that band covered, that's great. And we also observed that the DoD is actually using that, already today for 5G deployment. So there's stuff going on there where we have used already cellular technology. Of course, it's all super classified what's going over there, but it's being used. So therefore, the band in principle could be reused, but we need a little bit of a push from a federal point of view to make this happen. Same challenges as before to get that coexistence going. There's a bit of satellite in there as well. The challenges are slightly different as well. Now, the nicest band we are really super happy about as a cellular community is 7 gig band, and it was a big fight because there's so much going on in the 7 gig band. Again, there's mainly federal stuff in there. We have point-to-point links, we have satellite links, we have NATO band. NATO is using it around the globe, but notwithstanding that, the international community has agreed to actually start looking at this band for WRC 27. So we need your help to work out how could a cellular system, high power, please don't start with 30 dBm per 10 meg, okay? Start at, how far can we push the envelope? How can they coexist with a system which looks into the sky, a system which has a very low angular impact like radar, and even ultra-wideband. Okay, even ultra-wideband, and then you'll say it's not our problem. Apple will disagree, and we'll, most of us use Apple in the US. If Apple says we can't use it, then there's a problem. So it will probably not come to that, but we need to find a way of making sure that if I'm transmitting the uplink, I'm not saturating the downlink on the ultra-wideband thing. They want to use it for car keys. They may want to use it for spatial situation. iPhone 13 onwards, they use ultra-wideband to understand what's going on in the room. You want to transmit your pictures. You want to the tethering service and all that. So there's a lot of stuff going on in the band. How do you make this work in an industry ecosystem? Everybody's super important. Nobody is better or worse than the other, right? So that's my challenge to make this work. So WRC was quite, I think we we reached what we wanted. I can't really speak for the Wi-Fi community nor the satellite community or the federal communities, but at least the IMT community is reasonably happy. This 7 gig band is important. The other bands as well, the 4 gig band, as you can see here, has been considered in Europe. There's also higher frequencies being considered. I didn't talk about this today at all, but they're also there. So hopeful, but we need you to contribute. So, and I'm going to close now with maybe some challenges. So let me start with the regulatory challenges, which are maybe not that pertinent to you, but still important. So we really need to get that roadmap accelerated as much as we can. We need to be more ambitious. Maybe the 2-year cycles are not even good enough. Okay, so we used to release chips every 18 months to 2 years. Now NVIDIA has shown us we can do it quicker. They're doing it every 6 months. Why not in the spectrum arena? So we need to accelerate these studies, green the model, get out, be more intense. And I think the CHIPS Act funding could catalyze that a bit. Let's not forget about the 4 gig funding, 4 gig spectrum band. We need to modernize federal use of the spectrum. If you look at the Shannon capacity limit, telecom's quite close. Federal is very far. Okay, so therefore we need to somehow do probably a little bit better, do some reforming and do some incentives as well. That we all recognize we need the radars, we need that equipment to work. So and sharing needs to work in one way or another. My colleagues insist that there's a lot of stuff we can do from a static or semi-static deployment today already. Okay, I personally don't have evidence. I haven't seen the data, but I trust them. They're very good engineers. So maybe we need to phase that into 3 phases, saying, okay, what can we do today from a static point of view, a semi-static coexistence, okay? What can we do from a reasonably dynamic point of view with a database potentially, a bit like the TU Whitespace CBRS model? And then what could we do from a more dynamic point of view? How far can we push the envelope? What needs to be done there? So that's from a regulatory point of view. Now, from an economic challenge, high power, the power is very important. And something we haven't talked about at all, actually, and I'm talking now as, the former CTO of one of my companies. So I co-founded a company, which is quite big in Europe. We're a market leader in B2B Internet of Things. So we are instrumenting all the highways, refineries, and all that. And there's one thing which is completely overlooked. You cannot use LoRaWAN, Sigfox. Well, Sigfox doesn't exist anymore. You can't use LoRaWAN or even Wi-Fi to protect your refinery. It doesn't work because that's license exempt spectrum. No insurer will underwrite that link because if somebody comes in watches a Netflix movie, okay, even if you use CBRS today and somebody else comes in with a CBRS solution, you're not protected. Link breaks. The valve is not able to tell there's a pressure building up, refinery blows up, whose fault is it? So there are very serious industrial challenges which, legally only work with the licensed spectrum because it's owned. There's somebody who's at fault if it doesn't work, and therefore insurance is underwriting that case. So please don't forget that there's more than just the issue of power and all that. So let's get that right. Spectrum harmonization, meaning make sure that the US doesn't have a band here, and Europe has a band here, and Asia has a band here, because that's a nightmare for the Qualcomms and the Ericssons and the Nokias and everybody else in the world, because we need to make sure that there's, Qualcomm will not build a chip for California. Qualcomm will not build even a chip just for the United States. They're really after the global market. They want to make sure that whatever chip they build can be put into any iPhone, any Android, Google phone, and it can be deployed globally. So let's harmonize that as much as we can. Let's make it as contiguous as possible, because as you go into contiguous mode, you are seeing that you get much more efficient on the side loops. You get a lot of spillover. Receiver standards become much more important if you don't have it contiguous. So there's a lot of extra secondary kind of collateral work which needs to be done if we don't get that right. So I think that needs to be really taken care of. And maybe that is for you. And as my closing slide, actually, what I really like you to do is whatever magic you do in the higher bands, whether that is millimeter wave, any of them, not only 26 and 28 gig, moving up to the other bands which are being considered now. What you do in sub-terahertz, the current W and D bands, whatever you do there, make sure it is applicable into our FR1 and FR3 bands, right? So anything from 2 gig to 15 gig, we massively appreciate if you can make that work. And you know, I'm dealing a lot still with students. I'm attending conferences, poster sessions, you know, and every time I see a reflective intelligence surface poster, super smart, and it's you know, at 100 gig, and I ask, you know, can we bring it down? The answer is no, and then we discuss. It turns out it's possible. So if you just use a little bit of intellectual firepower to think on how we can translate these challenges into the mid bands, you would help a big industry. Okay, a big industry. So therefore do that. Start thinking also, rethinking on how to redesign transceivers. We're getting so much more digital into the front end right now. We still don't know really how to build the wideband transceivers, you know, how to power them, you know, how to build power amplifiers in the first place, which are energy efficient, wideband and all that. A lot of challenge, and I think CHIPS Act will be a great enabler there to make that happen. And I'm in a few projects with some of you in the room. And last but not least, you know, get the sharing right, high power, and again, you will say it's impossible, but I think it's possible. You know, there's fascinating research being done. Let me give you one direction, and it's not an Ericsson endorsement. It's just Mischa telling you one thing which could be interesting, which is, you know, a whole area of which Muriel Medar actually has pioneered, the ground decoder, because you could apply essentially ground decoding scheme not only to noise but to an interference scheme which is out there, right? So, and we have Rabia here who's been, if you raise your hand, she's building the chip at the moment, you know, which are actually is a real prototype, right? So we have this stuff out there. Expand this intellectual firepower into that high power space. Use all the tools and innovations you have around you, and help us as an industry to move forward, equalize it. So in the end of the day, you can just flick through, you know, your Instagram reels a little bit better. But there are many other societal use cases. I'll leave you with that. Thank you very much, and happy to answer questions during the panel if we do. Right. Thank you.